All right, let's do this thing. Lesson 6. This is actually our final lesson of the unit. Am I sharing my screen?
Has this unit been a ball?
Oh my gosh. I guess I shouldn't say it's the end of the unit necessarily, because unit 6 is also trigonometry, but it's going to focus in on the identities that we learned last time. It's going to dig a lot deeper. But to do more of the identities, we want to throw in the other reciprocal graphs. I kind of ruined it. Reciprocal. Hey, Mr. Contreras, before we get started, why are you all looking warm?
Well, it's winter and it's been snowing quite a bit. So our theme for today is warm. And I actually have a tortilla blanket because it's fun. And plus, I like making tortillas, which is also fun. Highly recommend these. Let me know if you want a recipe.
I was going to say, how do you make a tortilla?
You just make some dough and you let it rest, and then you roll it out.
Do you pan fry it?
You heat it up like dry heat on the stovetop on a comal. So it's like just like a piece of metal.
Okay.
Yep.
Cool. All right. Let's get into this thing. We are graphing the reciprocal functions, starting with the reciprocal of sine. That would be cosecant, right?
Yes.
Yes. Sorry. So
not inverse sine.
Not inverse sine. Not sine inverse. Yes. Cosecant. So we're graphing cosecant here. How do we get the cosecant function from the sine function?
Well, it's just reciprocating, right?
What do we do for the reciprocating?
We look for ones because those are nice.
So one. Negative ones too, right? Yeah.
Are also nice, yeah.
Yeah, because the reciprocal of 1 is 1. Reciprocal negative 1 is negative 1.
When we have zeros, we have undefined.
Yeah. We're getting smaller and smaller and smaller, so reciprocal is getting bigger and bigger and bigger until we become undefined. Okay, I'll do that at all the undefined points. And then we got them over here too. All right. I like to do 1/2 as well.
Because there's a 2 right there?
Yeah. I mean, like it's our scale's all good. Let's just like turn this 1/2 right here into a 2. Reciprocal. There's negative 1/2 here. I'm gonna make that a negative 2. 1/2 there. I'm gonna make that a 2. The goal here is just to know what this graph looks like and to kind of determine some useful points when trying to mentally think about what the graph looks like. In fact, whenever I graph cosecant in my mind, I almost always imagine the sine graph and then do this process. And I've done it so many times that I can do it pretty fast, but I made a mistake over here. There. But I imagine the sine graph and I reciprocate in my head. But I'm a very visual person. I don't know if that's going to work for everyone. I don't know. This is what it's going to look like, though. What else? Can you graph the curves through my points?
I can try, but
I can also do.
We also have to keep in mind that boom.
Oh, nice. Well, I like that you chose purple, by the way.
These are very unsymmetric.
And for all intents and purposes, oh, that is not very symmetric. You are right. No. For all intents and purposes, I think this is enough points to kind of visualize the cosecant graph. We could reciprocate root 2/2 or root 3/2, all those, but I don't think that's necessarily worth it here. The goal here is to know what the cosecant graph looks like. It's really important that we understand this graph as well, too, because we've been dealing with the inverse functions lately. And soon enough, we're going to dig deeper into the inverse functions, one of which being the inverse of cosecant. It'll be particularly annoying if you don't really know what cosecant looks like to then start to think about the inverse of cosecant.
That's true. Because like, how are you going to reflect something that you don't even have in your brain?
Exactly. It's kind of like logarithms. Like it's hard to understand what a logarithm is if you don't really understand exponentials. This second unit that I'm talking about, this unit 6, this identities unit is going to rely very heavily on the cosecant function and its inverse, the inverse cosecant function, arc cosecant. Cool. So we have it. There we go. Oh, you grabbed me, and I saw it before you said boom. Okay. What are some properties here? Let me actually zoom out for this part so we can look at the graph while identifying properties.
Okay.
Boom. It's like, what's the domain here?
I think it's all our real numbers except for where our sine is 0. So then our arcsine, or our, not arcsine, our cosecant is going to be undefined. So when is that happening? At 0?
At 0. At pi. At 2 pi. Negative pi. Negative 2 pi. Negative 3 pi. 3 pi. 4 pi. 5 pi.
So integer times pi?
Yeah, pi. And this is how I like to write it. Some people write k pi. Some people write pi n. I'm going to write pi k, where k is an integer. And then from here on out, I'm not going to write k as an integer. I'm just going to write pi k. Just let's kind of like at the top of this document say k from here on out is an integer. Cool. Range.
One thing about what you just wrote, Mr. Kurt, the comma is one way that people like show that our set notation is saying such that. But another way that we say such that in math symbols, and it just varies based on who wrote the book that you started using first, is like that long line, right? Such that. And then I think maybe there might be some people who use colons. Not
yeah, and
sure,
also
though.
The abbreviation S.T. That's actually when you started talking, I'm like, are we going to go S.T. But no, the bar, we used the bar way back when. Let's continue to use that. Let's be consistent. Thank you. All right, we're going to dig really deep into this one, and the other ones we'll look at it a little bit more casually. How about the range?
The range is all the real numbers except for what is strictly between -1 and 1.
So I want to parentheses, right? Because I'm removing everything, but I don't want to remove -1 and 1. There are other ways we could have written this. I could have also written this. This is congruent. If you guys remember that symbol, this is congruent to. Let me actually zoom back in. This is congruent to just -infinity to 1 inclusive -1 union 1 to infinity. Both are valid ways. All right. How about the this is actually a commonly mistaken one. What about the period here?
So is it going to be 1 pi because that's like the top part? Is it going to be? Go ahead.
I was just going to say those asymptotes are almost like a distraction. So, is it pi? What do you think it is?
Well, in order to hit something that can be repeated, we need to be both like the top part and the bottom part because that whole thing gets repeated, right?
Yeah, let me do this.
So 2 pi.
Here's this point. Here's this point. That is the next time I repeat.
Oh.
So that's, what is that? 2 pi?
I think so.
A little bit less than -pi to a little bit less than pi, 2 pi. Yeah, be careful. Those asymptotes are a distraction. It's not actually every pi, it's every 2 pi. How do you feel about amplitude?
Can amplitude be infinity?
I don't know. I feel like the definition of amplitude is the distance from the midline to the maximum. That's how we defined it before, right? So I feel like the amplitude is like not applicable here, right?
Right. Because there is no maximum.
Can we think of the amplitude as something though?
Maybe like the distance between our like caps and our cups.
Like our yeah, I don't know how to describe those. Our yeah, what this thing and this thing?
Yeah, I said cap and then I said cup because that's what we use in comedy for those symbols.
Oh, true. / cup and cap. Let's go with half that, just like it was half in the sine curve. Right? It's like a midline to max. I think that's going to be useful because later on we're going to graph the cosecant graph. And just like with sine and cosine, let's get ourselves a midline. And then let's look at the number, the coefficient of the whole function. That's how high you go up to get to your cup. And you want to go that low to get to your cap. So let's write NA just to be exact, but
I'm putting on a cap.
I know.
And then I'm going to put a cup over my head.
No amplitude, but we can use that coefficient in the function later on to determine how to graph it. We do have asymptotes, though. We've established those. Pi k.
Pi k?
That's what we removed. Midline. I think we do have midline here, right? I guess like the distance between the max and the min divided by 2 doesn't really make sense here. Let's go ahead and say y equals 0. These are all, every explanation might be a little bit different depending on definition. Max and min.
We have relative maxes and mins at all of our, what is that? K pi over 2?
Rel max of -1 though, right?
Mm-hmm.
On this interval right here, -1 is a relative maximum.
Mm-hmm.
And then 1 is our relative min. That's kind of funny. And then are we bounded? Not really, right? Yeah. Nah. There we go. There's the cosecant graph, everyone. Take a little mental picture of it. Right? But I think the key is, think about where sine is 0. That's where your asymptotes are. And then you just need to put your cup and your cap in the right spot. I'm like 100% on board with this cup and cap thing.
Nice.
I'm going to use it for years. Unless, of course, someone comes up with something better. All right, let's keep going. The reciprocal of cosine is?
Secant.
Secant.
Oh.
All right, we're graphing secant here. And as cosine looks like, I have something to say. Sine and cosine are shifts of each other, right?
Mm-hmm.
Can we know before doing this that secant and cosecant are going to be shifts of each other?
Yeah.
What's the identity?
I don't know.
Cosecant of x is equal to what of secant?
Do you remember? Pi over 2.
Pi over 2?
Minus.
And we can like work some magic. And what is secant even or odd?
Secant is even.
So I can pull that negative out. Secant is x minus pi over 2. It's also pi over 2 minus x. Cosecant is just a shift of secant by pi over 2. So we could, if we wanted to, not do all this reciprocating and just do a shift.
Can we just copy it? Is that a thing?
I don't know. Do you want to try? That sounds like maybe a headache. Are you trying?
I'm trying.
How long can Mr. Kirk hold a drum roll?
I think it's because you drew parts of it. I can only interact with parts of it.
Yeah, that sounds annoying. Let's just get it real quick. All right. Asymptotes where it's 0, right?
Yep.
And if we really want to, we can look at just one period because it's just going to repeat itself.
Mm-hmm. So
that's kind of what I do is I imagine one period. And that's how I remember where cosecant and secant are. In fact, sometimes for speed trig, I actually imagine the secant and the cosecant graphs to get the answers. I'm going to get this one over here.
Oh, am I doing that? I don't know if I'm doing that.
Oh, I almost like went through your dot.
Cool.
Oh, I didn't go through that dot though.
Less.
I'm going to get the one over here. There's 2.
I'm doing the cap on that.
Okay, and I'll do the cup.
I like this vocab. It's nice. It's helpful.
Yeah, it is actually. Language is so powerful.
Boom.
Sweet. right, so here's the secant graph, and it's just a shift of pi over 2 of the cosecant graph, which is how you can think about it. I like to just imagine the cosine graph since I just have a strong grasp of that, and I reciprocate it in my head. Instead of let's listing the properties, what do you think? I'll make sure the properties are there in the answer key, but just what comes to your head when you look at this thing?
It's pretty much like most things are pretty similar. The only thing is that we're shifted. So we just need to keep in mind the shifts and then we're good to go.
Asymptotes. Pi over 2 plus pi k. Still every pi k, but shifted pi over 2. Yeah. We have this space in the middle that is never gotten to. I think one thing that overlaying these two graphs doesn't do the best job of is talking about this empty space. You know?
I guess so.
I don't know. Do you have the ability to remove the cosine graph and see just the secant graph?
Like with my mind powers?
Yeah, with your mind powers?
Yeah, I think so. Just kind of like, just think about it, like pop it off. But we can do, some students did this thing where they would draw over something with a with like a white line on.
Oh, are you doing that right now?
I'm trying.
I love that. The one way to erase in Kami.
Yep.
I'm waiting for the drop.
It's slow going. But this is, I thought, a very clever way of leveraging our digital tools. Although I am erasing some parts of our.
Yeah. Well, while you do this, I'm going to make a comment just for the students. We've been working in groups lately, and one of the critiques was the inability to edit other people's comments and annotations. And I think that's actually a good thing. We don't want to remove other people's work. We want to comment on that work. That's one of the cool things that Kami has the ability to do. So if you see something that you think might be wrong, take advantage of that comment tool. Right? Well, the goal here is not to necessarily get the correct answer every single time and turn in a perfect sheet of a perfect problem set. The goal is to have those conversations and to critique each other in a positive way. So instead of worrying about being able to change other people's work, think more about how can I positively critique the work that I'm seeing using the other tools in Kami.
Constructive feedback.
Yeah, constructive feedback.
That's something that we're all trying to grow in.
Yeah.
And it's helpful.
One
more thing about just leaving comments, that if you're concerned that maybe like something you write might not have the right tone, you just record an audio comment. Just
with your tone.
The like, I'm not sure if this is the right, and then it's okay.
The goal here is to have those conversations and to learn from each other, not to turn in perfection. Right? We are not robots, as I've said many times. All right, so there are properties here. We'll let you think about them, but we've said some of the major ones, asymptotes. Let's continue. All right. So there was something we haven't done. Then in a normal brick and mortar year, we probably would have done by now already, but we have not looked at the tangent function yet. So we're going to look at both the tangent function and the cotangent function at the same time. So Mrs. Contreras, I just wanted to set us up. We don't know what tangent looks like yet. We're going to have to be a little bit more slow about this page. What do you feel in tangent? What color?
Probably like Grover blue.
Let's go Grover blue. And then we'll do cotangent in Elmo red.
Elmo red. Yeah.
Those will contrast really nicely, I think. And then actually, you know what we could do? I'm going to graph tangent. And I want you to graph cotangent because at the end, I can toggle off what I've written so that we can see the cotangent graph by itself. We're going to graph the tangent function. And I'm going to do that so that we can toggle it off later. And then you'll graph the cotangent function and we'll leave it toggled on.
Okay. Not sure I'm totally understanding what you're saying, but.
Do you trust me? You're willing to roll with it? Okay, cool.
Yeah, let's go.
All right. So I'm going to graph tangent. Tangent of 0 is, I'm going to get a little unit circle here. That might help us. What is the tangent of 0?
Tangent of 0. So that's going to be our slope, which is 0.
Yeah, so tangent of 0 is 0. And then moving up, let's get pi over 6. What's the tangent of pi over 6?
Pi over 6 is going to be 1/2.
1/2. So it's going to be right there. How about pi over 4?
It's 1 over root 2.
1 over root 2, which
No.
is, oh, no. Pi over 4 is 1,
1.
right?
1.
Yeah. 1. And actually, let's rewind. Tangent of 0 is 0. Tangent of pi over 4 is 1, but tangent of pi over 6 is not 1/2. I think we were mixing up with sine.
With sine,
So,
yeah.
Yeah. It is, the coordinate is root 3 over 2, comma 1/2. So we have 1/2 over root 3 over 2. 2's cancel. Root 3 comes up. Root 3 over 3.
Nice.
Root 3 over 3. Or we could have left it as 3 over root 3. Or no, 1 over root 3.
1 over root 3.
Quick calculation, just for my very insane brain. Root 3 over 3 is square root 3 divided by 3 is 0.57. So it's almost 1/2. Boom. All right, and tangent of pi over 3 is root 3. That is 1.7. What happens as I go to pi over 2, though?
Undefined.
Undefined. The slope is vertical. So that's where we're going to get that point. The slope gets bigger and bigger and bigger and bigger and bigger without bound. How about on the other side of pi over 2?
So isn't it just the, is it going to be like negative, like way down?
It's going to be like, yeah, it's going to be super duper negative, right?
Mm-hmm.
We're going to have like an infinitely steep going down slope. Then we're going to come back up. I think we're going to be at negative 1.7. We'll be at 1 there, and then we'll be at 0.57 there. And then at pi, we're at 0 again.
We're at 0 again, because we got a flat slope.
What's the period of pi? Oh, I just said it.
The period of tangent is pi.
The period of tangent is pi. So
we're just going to copy that over.
Copy that over, yeah. And actually, let's see if I can do that using what you just said earlier.
It might work.
It might just work. Boom. Oh, that's a lot. I don't want all that. No, I just want. All right. I don't think that's going to work. It's craziness. All right. I'm just going to do it. We're going to be around there, there, there. And we shoot up. And we have another slope there at 3 pi over 2. It says 3 pi. It's really 3 pi over 2. Then over here, we're going to be roughly there, roughly there, roughly there, asymptote. I'm going to stop there. Boom. Fun fact, the slope at 0 is 1. Just for anyone who cares about that kind of thing. It doesn't level off. The slope is 1. Calculus explains that, but we're not going to get into that.
Yeah, I was about to say, like, wow, Mr. Craig, I thought we were in pre-calculus.
I want to differentiate it a little bit from I want to differentiate it a little bit from the x cubed graph. Right, the x cubed graph has no asymptotes, first of all, and also it completely levels off at 0. We talked about that a long time ago. Here it doesn't. It actually hits a slope of 1 and then turns back around. All right, this is what I was saying earlier. Can you now draw us the cotangent graph?
I will do my best. So I'm going to be efficient, lazy, I don't know, one or the other. And I'm just going to drop in vertical lines.
Sweet. Should we switch over to you sharing, or should we just keep doing what we're doing?
I think it's okay.
Okay. So we have those vertical lines. Those are not part of the graph, everyone. Those are just asymptotes.
Asymptotes. And then, can I make that?
Nice. Oh, I see. You're turning them into dotted lines.
Yeah. But then I'm confused, Mr. Kirk, because when you have something that is an asymptote, what am I going to have?
So let's just do the cotangent. What is the cotangent of pi over 2?
Cotangent of pi over 2 is 0.
0. So let's put a 0. Right?
Okay.
Tangent and cotangent are reciprocals except for at those undefined points. At that point, we are defined. So a little bit backwards from our definition of reciprocal a long time ago, but cotangent is defined because it's defined by the unit circle before being defined as a reciprocal.
Okay.
All right.
And then for our ones, well, that we can still keep at 1, right?
Mm-hmm.
And the same with our negative ones.
Yeah. And let's see, the reciprocal of 1.7. It should be about 0.57, right? It should be the reciprocal of the other one.
So like something.
The reciprocal. That to the negative 1. I'm in my calculator right now. Yep. So the reciprocal of, they're going to match right up like you have. Can you move this one red dot over one tick mark?
Yeah.
Thanks.
Like that?
Yep. Cool.
Cool. So then can we just like
connect the dots?
Oh my gosh, so challenging.
Nice.
I know the anticipation is just killing you. Ah. Oof. Did it work?
Yeah. It's really nice. Can you continue the tangent graph on the left-hand side?
Cotangent? Yeah, absolutely.
The cotangent? Yeah.
So what do we get? We get
it's going to be like 0.57 at the negative pi over 3.
Like that.
Gorgeous. Gorgeous. Yeah, of course, it continues.
You want an arrow? I think arrows are responsive.
These look really similar, right?
They do. They almost look like they're reflected.
Oh, wait, let's look at the identity that we talked about earlier. Well, we talked about it with cosecant and sine, but tangent of theta is equal to what in terms of cotangent? Think about the cofunction identities.
Mm-hmm. And I don't think I stored those in my brain as rarely as I should have.
That's no complementary. Co stands for complementary.
Mm-hmm.
It means they add up to 90 degrassies or what radians?
Pi over 2?
Pi over 2. Pi over 2 minus theta. Watch this. Cotangent. I'm going to rewrite it as negative theta minus pi over 2, like I did with the secant.
Valid.
And is cotangent even or odd? Not based on, we could use this picture, to be honest.
It's odd.
It's odd.
So then the negative.
Yeah, so the negative actually pops out.
Mm-hmm.
So cotangent is not just a shift. It's a shift of pi over 2 and a vertical reflection. If we shift the red graph to the right, pi over 2, and then reflect over the x-axis, we are on top of the blue graph. It's good stuff.
Oh.
So we have the geometric interpretation, but we also have the algebraic interpretation in the top right corner there. Hopefully, oh no, with the new way we're recording, that won't be hidden. Remember back in the day when that was hidden? Everything in the top right corner.
Mm-hmm.
So this is why I had you graph it and not me for the red one. I'm going to turn off you. That's the tangent graph.
That's so cool. I didn't know you could do that.
I just clicked your initials down there in the bottom.
Whoa.
And then now I'm going to click on yours. So we have the tangent graph there. Goes through 0, 0. And then goes from negative infinity to positive infinity. I'm going to turn off mine.
Wow.
There's yours.
Cool.
All right. So if anyone wondered how I know what work you're doing in the group work, I unhighlight everyone's and I can see who's done what. So make sure you're doing your fair share. And that goes for not doing too much, also not doing too little. Work well in groups. All right, we have our tangent and our cotangent graphs all in one. Boom.
How did you find that out, Mr. Kirk? Did you just like click on it one day? And then
Yeah, that's exactly how it went.
Wow, that's so
Yeah.
cool.
Yeah.
Nicely done.
I'm glad I can share that with you. All of the students are like, no. All right. One of the things that teachers do is we hold you accountable.
Mhm.
All right, I want to see the best work that all of you can do. Cool. Now you know why I was saying all those weird things earlier too, which is
Yeah.
sweet. All right, so we got tangent, we got cotangent, we got secant, we got cosecant. We got a bunch of new graphs. We want to try to internalize them and be able to think about what they look like. All right, if you're like me, I just think of the first three and then reciprocate the picture for the rest. But whatever works for you. How do you think you're going to think about them, Mrs. Contreras?
I think I'm going to use sine or tangent as my anchor points and then do shifts and reflections accordingly.
Sweet. All right. I'm going to pause here. Actually, let's close this video out.
Cool.
Is that cool with you? Let's close this thing out. Stop my share. We got the new graphs. The next step is to be able to transform them. We're going to transform them like we transformed all other graphs. Dilations, translations, all that kind of stuff. And we already did it a little bit here today. But we're about to move into in my opinion, the hardest unit of the year. That's, of course, my opinion. But knowing these graphs, what they look like and their properties is what the past six lessons have been all about. So I hope that everyone at least understands the material we've done up to now so that we can move into this next more challenging unit.
Cool.
Cool. Are you warm?
I think so. Yeah.
Awesome.
I'm good.
Cool.
Are you?
I'm actually pretty toasty.
Nice. What's your favorite kind of toast?
I have a follow-up question, but my favorite kind of toast is sourdough. What do you mean? Like what? Is that a different question than what? Is that a different question than what's your favorite bread? Or is your favorite bread different than your favorite bread that's been toasted?
Yes, because I think milk bread is very nice, but toasted milk bread is not as nice in my mind as French toast.
Oh, I'm gonna go with the cinnamon swirl bread, cinnamon bread. That stuff is delicious toasted. My follow-up question is: at what point in the toasting process does bread turn into toast? My old boss, when I used to work at a music center, said it was 17 seconds, regardless of machine.
What?
Yeah.
So much.
17 seconds. I didn't
use like a machine though. I just use a kamal. Just heat it up on the stove and then put a piece of bread on it.
17 seconds of that and it's become toast. Before that, it's still bread.
I think as soon as you can see some
discoloration.
Yeah.
All right, let's close this one out.
Coloration.
We have now posed two incredibly philosophical questions. What is the best bread toasted, and when does bread become toast? You want to close it out?
Yes.